Today we're going to talk about inverse functions. So what we see pictured to the left here is a picture of the function f. It has a domain, it has a range, and then f has rules that associate something in the domain to something in the range, and those arrows show where things are going. F inverse just attempts to reverse the arrows. So if we have an element x that f takes to f of x, f inverse takes that same element back to x. And what we can see here is that means that x, f of x, f inverse of that is x, right? X, f of x, f inverse back to x. Now if we start in the other set, x, f inverse takes it to f inverse of x, f takes us back to where we started. Okay, and this gives us the relationship f of f inverse of x equals x. And these are the two fundamental relationships that define f and f inverse. Now, if you actually look at this picture over here, you can see that the domain of f is the range of f inverse, and the range of f is the domain of f inverse. So these two identities, f inverse of f of x equals x, f of f inverse of x equals x, and the fact that for inverse functions, the domain and the range switch are important characterizations of the inverse function. So for example, if f of x is x cubed, f inverse of x is x to the 1/3, and we can see this by calculating f inverse of f of x, which is f inverse of x cubed, which is x cubed to the 1/3, which is x, and the other relationship, f of f inverse of x, is f of x to the 1/3, which is x to the 1/3 cubed x. These two functions are inverses. Now, if we look at the picture here, we can see that here's the graph of y equals x cubed, and here's this point 2, 8. So f of 2 is 8, and 2, 8 is on this thing. Now, the inverse has to take 8 back to 2. Remember, that's the story here. F followed by f inverse gets you back to where you started. So f of 2 is 8. F inverse of 8 has got to be 2. And that means this point 8, 2 is on the graph of f inverse. Now notice what's happened. The graph of the original function has 2, 8 on it. The graph of the inverse has 8, 2. X and y have switched. And you can, as a result of that, if you know f, draw the graph of f inverse by just taking the point xy and switching it to yx. Now there are times when you cannot find an inverse function. So let's look at the picture here. And what we see here is there are a couple of points that are carried by f to the same thing in the range. If we try to draw f inverse, we have to have two arrows coming out of that point. This is not a function. And what we can see here is the problem here was a and b go the same place. F of a equals f of b for a not equal to b. And when we tried to draw the inverse, it didn't work. So if f of a equals f of b for a not equal to b, there is no inverse function. And we have a special name for functions where that doesn't happen. F of x is called 1-to-1 if whenever a is not equal to b, f of a is not equal to f of b. So this picture here is not 1, 1. So, and the reason is there are two arrows going in to the same point. So you've got a 1, 1 function exactly when everything over here has only one arrow going into it. f inverse exists for f of x exactly when f of x is 1 to 1. Now you may recall that when you were testing functions, you had this thing called the vertical line test. And the idea was if a vertical line crossed the graph at more than one point, you didn't have a function. And the reason was one x value gave you two y values, which is not allowed for a function. For one-to-one functions, we have the horizontal line test. If a horizontal line crosses the curve at more than one point, you don't have a one-to-one function, and you can see that here. Both of these points, x1 and x2, have the same y value, not one-to-one. F of x1 is f of x2 is y. Now, if we look at these pictures, you can see that the difference between this curve, which is just sort of always increasing, and this curve is this decreases, then it increases. There's actually a local minimum here, and if you think about it, if you've got a local minimum and you draw a little line right above it, it's going to cross twice, and the same thing is going to be true with the maximum. So we call f of x increasing if whenever a is bigger than b, f of a is bigger than b, f is decreasing. Whenever a is bigger than b, f of a is less than f of b. These are exactly the functions that are going to pass the horizontal line test. So a continuous function is one-to-one if it's either increasing or decreasing. It cannot have a local maximum, or can it have a local minimum? And of course, for differentiable functions, the derivative is going to tell us whether f of x is 1 to 1. So for example, y equals x cubed, which we know has an inverse already, so this better be 1 to 1. Y prime is 3x squared. There is a critical point at 0. However, if you chart this, you'll discover that 3x squared is positive when x is less than 0 and positive when x is greater than 0. So even though there's a critical point, this is an increasing function because it goes up to the critical point and then goes up away from the critical point. Y equals x squared, y prime equals 2x. You'll notice here the derivative is negative when x is less than 0, positive when x is bigger than 0, down then up, local minimum, not 1 to 1, and y equals x squared doesn't have an inverse. However, if we decide to take y equals x squared for x greater than or equal to 0 only, in other words, we're restricting the domain of f of x equals x squared, we only get the right-hand side of this picture, and it's increasing, and that means there must be an inverse, and the inverse turns out to be the square root of x, which is not a big surprise. And we check that. F of f inverse of x is f is the squaring function. F inverse is the square root. The square root of x squared is x. The other direction, we have f inverse of f of x is the square root of x squared, and now the square root of x squared is x since x is bigger than or equal to 0. If we allowed x to be negative, then the square root of x squared might be minus x, and we'd have a plus or minus x, and that's why we would run into trouble. But since we've restricted the domain to x greater than or equal to 0, this works just fine. Now, let's talk about finding inverses. So let's start with this function f of x equals 3x plus 2. We calculate the first derivative. It's 3. That means that this is an increasing function because f prime is positive everywhere and it's 1 to 1. It's going to have an inverse. How do we find the inverse? If f of x is y, then f inverse of y is going to be x, which means we take this equation and we solve it for x, and what will appear on this side should be f inverse of y. So we start with y equals 3x plus 2. We subtract 2 from both sides, and then we divide by 3, and we've got x equals y minus 2 over 3, and that should be f inverse of y. And if we want it to be f inverse for x, we just put in an x every place we see a y, and here is f inverse of x. Okay, so the process here is write down y equals f of x, solve for x, switch the x and y, and you've got f inverse of x. Now let's just check to see that this has actually worked. F of f inverse of x is f of, and now f inverse was x minus 2 over 3. F takes whatever you put in here, multiplies it by 3, and adds 2. And we do that. 3 times x minus 2 over 3 is x minus 2 plus 2. We get x. And now the opposite direction, f inverse of f of x is f inverse of f of x, which is 3x plus 2. F inverse takes whatever you've got, subtracts 2, and divides by 3. So we get 3x plus 2 minus 2 over 3, which is 3x over 3, which is x. So we have indeed found the inverse. So the next thing to talk about is the derivative of an inverse function. If both the function and the inverse are differentiable, we can find out about the relationship between them by differentiating the equation f of f inverse of x equals x. Okay, we do this using the chain rule. Okay, so f prime of f inverse of x times the derivative of f inverse of x, which is just the derivative of f inverse of x, equals the derivative of x, which is 1. And now we can solve this for the derivative of f inverse. And we get the derivative of f inverse of x is 1 over f prime of f inverse of x. Now, let's see what that means. So let's go to our standard example. F of x is x cubed. F inverse of x is x to the 1/3. Let's see how the formula relates the derivatives of the two. And we know that f of 2 is 8, and that f inverse of 8 is 2. So if we look at the relationship here, what we're going to get is f inverse prime at 8 is going to be 1 over f prime of f inverse of 8, and we know that f inverse of 8 is 2. So it says the derivative of f inverse at when x equals 8 is 1 over the derivative of f when x equals 2. And now let's see what's happening graphically here. F of x is x cubed, f prime of x is 3x squared, f prime of 2 is thus 12. And we look at our graph here. Here's our point 2,8. And there is our slope of 12. Now let's look at f inverse. F inverse of x is x to the 1/3. F inverse prime is 1/3 x to the minus 2/3. 1 over 3x to the 2/3. If we put in 8, we get 1 over 3, 8 to the 2/3. And 8 to the 2/3 is 4. So we get 1/12, which you'll notice is the reciprocal of that. And now we look at our picture here, and this is our point 8,2, and this is the place where the derivative of f prime is at 12. Then you can see essentially what's happened here. The point 2,8 on f corresponds to the point 8,2 on f inverse, because x and y switch roles. But if you think about it, slope is change in y over change in x. If x and y have switched roles here, then we should have a change in x over change in y from here being the change in y over change in x here. We get a reciprocal. And that's in fact exactly what this formula is telling us.